George, Year 2. Interactive Continuous Learning of Visual Concepts. This is our robot George. We want it to operate in real-world settings, communicate with humans, and acquire novel knowledge in a natural way. In this video, we focus on interactive learning, specifically on 3 types of interaction with a tutor that lead to knowledge updates. We demonstrate these learning mechanisms on the case of learning object properties, such as object colors and 2 basic shapes, in a fully embodied and situated system. So let's see how George learns about object properties.
Hi, George.
Hi.
Is this green?
I don't know.
George is able to detect and segment the object, but he fails to recognize it. George doesn't recognize anything because he has not formed any models of any concepts yet. Let's teach him.
This is a green object.
Thank you.
The model of the property green has been initiated.
This is a blue object.
Thank you.
It is also elongated.
Thank you.
The models of another 2 properties, blue and elongated, have been initialized, each associated with their respective visual features. By introducing more and more new objects, and by teaching the robot, new representations of visual concepts are formed and keep improving over time. The visual concepts are represented as generative models, probability density functions over the feature space. They are constructed in an online fashion from new observations. In particular, we apply an online discriminative kernel density estimator we have developed to construct these models. The ODKDE estimates the probability density functions by a mixture of Gaussians and is able to adapt using only a single data point at a time. It also automatically adjusts its complexity by constraining discrimination loss and does not assume specific requirements on the target distribution. Therefore, during online operation, a multivariate generative model is continually maintained for each of the visual concepts. Feature selection is continually applied to mutually exclusive sets of concepts to determine the appropriate feature subspace for each set. When the models are reliable enough, George can take the initiative and ask for clarification whenever he can recognize an object but is uncertain.
Is this pink?
No.
Thank you.
George is able to correct his knowledge, or in other words, he is able to unlearn the previously acquired representations.
What color is it?
It is orange.
Thank you.
George asks open and polar questions, depending on the level of uncertainty of his interpretation.
Is it compact?
Yes.
Thank you.
George can also use object properties to refer to an object, when several objects are present in the scene.
Is the color of the elongated object blue?
Yes.
Thank you.
Every time George gets information about object properties, he unlearns or updates his representations accordingly. In this way, George can ask for information by referring to the objects present in the scene. George can also inspect his internal representations and detect gaps in his knowledge. He then asks a question that does not relate to the current scene, but that helps to provide the information needed to fill the knowledge gap.
Could you show me a white object?
Yes. This is white.
Thank you.
Using different types of learning, George improves his knowledge and answers questions that he could not answer before.
What is this?
It is an elongated green thing.
Up until now, we have shown what our system is doing. Now we will also show how it works. To summarize what is going on, let's look at the robot from the system's perspective. The system is composed of three main subsystems, or as we call them, subarchitectures. The visual subarchitecture processes visual information and detects and recognizes the objects. The dialogue subarchitecture takes care of the dialogue processing and communication with the human. Both architectures produce the beliefs about the world that are stored in the binder subarchitecture. These beliefs are then used by the planning subarchitecture to plan and execute the actions. Now let's look at the processing pipeline. What happens in the visual subarchitecture when a new object is introduced to the scene? George has stereo vision and observes the scene using two cameras. From two color images, a disparity map is obtained, yielding a cloud of 3D points. Then, a dominant plane is estimated by robustly fitting a plane to the 3D points, and groups of points sticking out of the plane are detected as spaces of interest. Objects are then segmented using the GraphCut segmentation algorithm, which is initialized using color as well as 3D information. Individual segmented objects are then subjected to further processing. George extracts low-level visual features and uses them to recognize the visual properties of the object. Let us now summarize this process from the processing point of view. First, from a stereo pair of images, a color image and a 3D point cloud are obtained. Then, using the bottom-up attention mechanism, spaces of interest, or SOIs, are detected. SOIs are analyzed and segmented, and proto-objects are created. They are processed further by an object analyzer, which recognizes the object properties. On request, at this level, the models of the visual concepts are also updated or unlearned. A visual mediator then packs the visual information and forms the robot beliefs about the perceived object and the status of the models in the binder. Multiple non-occluding objects in the scene can be perceived. When new objects are added or removed from the scene, the private beliefs are added or deleted correspondingly. The beliefs can also be altered by the dialogue subarchitecture through dialogue processing. First, the system analyzes an incoming audio signal using the Loquendo speech recognition software. Then, it parses the created word lattice and chooses the contextually most appropriate meaning representation for the utterance. Then it establishes which meaningful parts might be referring to objects in the visual context. The actual reference resolution then takes place when the dialogue interpretation is performed, taking into account the information stored in the robot beliefs. In this process, we use weighted abductive inference to establish the intention behind the utterance. As a result of this, an attributed belief containing the information asserted by the human is constructed from the meaning of the utterance. The dialogue production is triggered by generating a robot intention, which is converted by the dialogue manager into a communicative intention. The proto-logical form is then created, and an utterance in the form of an open or a polar question is then generated. The utterance is finally synthesized using the Mary text-to-speech system. The dialogue subarchitecture also takes care of answering questions. The dialogue manager receives the requests in the form of user intentions and generates the corresponding answers in the form of communicative intentions by using the information stored in the private beliefs. The beliefs are therefore the central information structure in the system. They are stored in the binder, which serves as a central hub for the information gathered about entities currently perceived in the scene. The binder receives the information about the visual objects and their properties in the form of private beliefs from the visual subarchitecture. Another epistemic object stored in the binder is the model status, which stores the information about the current models of colors and shapes. The third type of epistemic objects, the attributed beliefs, are created by the dialogue subarchitecture and model what the robot believes that the human believes, while shared beliefs model the common ground on which the human and the robot agreed and are used for reference resolution and generation. The beliefs stored in the binder form a basis for further reasoning, planning, learning, and communication about the real-world entities. Based on these beliefs, the planning subarchitecture plans for new actions. The planning subarchitecture is composed of 3 layers: motivation, planning, and execution. The goal generator in the motivation layer monitors the beliefs in the binder and based on them generates epistemic goals. These goals are then filtered, and the most important goals are selected. These active goals are then sent to the planner. The planner converts the private beliefs into the planning state and produces a plan that should satisfy the given goals. The goal management continuously manages goals according to their priority, eventually interrupting execution if a higher priority goal shows up. Plan execution proceeds according to the continual planning paradigm, monitoring the system's belief to trigger replanning if required. There are 2 types of actions that the system can execute. It can send a learning request to the visual subarchitecture to update its models, or it sends a clarification request to the dialogue subarchitecture to generate a corresponding question. The described mechanism naturally supports 3 types of learning shown in the first part of this video. We will now look in more detail at what is going on the system level. In the case of the situated tutor-driven learning, the attributed beliefs are taken as learning opportunities, eventually leading to epistemic goals that require that this new information is used to update the visual models, which triggers the update of the visual representations.
This is a green object.
Thank you.
This type of learning has the highest priority, enabling the system to immediately respond to human input. To implement the robot-initiated tutor-assisted learning, the planning subarchitecture also continuously accounts for the goal of maximizing the system's knowledge in terms of reducing the uncertainty of the detected visual models. By analyzing the a posteriori probabilities of detecting visual properties for every detected object in the scene, the visual subarchitecture estimates the gains of updating the current visual models. These gains are stored in the private beliefs and are monitored by the motivation management. The visual properties with the highest gains are selected, and a plan for obtaining the necessary information to perform the updates of the visual models is created and executed. The execution involves sending a clarification request to the dialogue subarchitecture, which is then subsequently synthesized, typically as a polar or open question about a certain object property, and the tutor's answer is then used to update the models.
Is the color of the elongated object blue?
Yes.
Thank you.
In the non-situated tutor-assisted learning, the learning cycle is also triggered by the robot. However, here it does not refer to the objects in the scene. The robot analyzes the current representations of the visual concepts, detects the gaps in these representations, and asks the human to show an object that would help to fill these gaps.
Could you show me a white object?
Yes.
These 3 types of learning and the mechanisms and representations that support them form the core of the George system. They enable the efficient acquisition of conceptual models in an interactive learning process that is not overly taxing with respect to tutor supervision and is performed in an intuitive, user-friendly way. The presented system is our second implementation of George. It is not yet perfect. It is not as robust as we would want, and the set of visual concepts that are being learned is relatively small. However, it implements the main learning mechanisms in a principled way and facilitates further extensions. Furthermore, the presented functionality is just a subset of a larger set of robot competencies we have been developing in the CogX project. By integrating them in George, the robot will gradually become more and more competent. Building on this system, our final goal is to produce a robot that self-understands and self-extends.